In this video, we're going to look at torque and then a few applications of torque. So in order to look at torque, first we have to define it. And torque is defined as a rotational force around an axis. Now, in order to understand what I mean by rotational force around an axis, you have to understand the difference between translational movement and rotational movement. Translational movement is when a linear force is applied to an object and that object then just moves in a straight line. So if there's, say, something on the floor and you push it and it just slides along the floor, that's translational movement. Rotational movement, on the other hand, is when something has an axis, could be fixed, maybe not fixed, but when a force is applied to it, it rotates around that axis instead. So let's look at this with an example here and illustrate it with a lever. So I'm just going to have make a lever here, and here's the axis for my lever, all right? And then here's just the lever itself, all right? And let's say that right here in the middle of my lever, I have some sort of a weight, all right? And that's going to be my resistance then. And then somewhere over here on the end of the lever, I have some force that is also applied to that lever to move that resistance or to move that weight. So in this case, this resistance or this weight, the way it provides resistance is by way of gravity. So it would have a center of gravity, and then acting on that center of gravity, gravity would produce a force vector that looks something like that. On the other hand, I could have a force over here where it's applied to the end of the lever, and that force is shown by this vector going up that way. And so you can see here we have resistance that is pushing this lever around its axis downward, but then we have a force that is applied to rotate the lever in the opposite direction. If you just kind of look at this example, it might look somewhat familiar to you because this could also be, if you wanted it to be, a wheelbarrow. And so if that helps you kind of understand how that works, that would be one common example of how this particular level would work. So this is what we would call a class 2 lever. And the different classes of lever are defined by what is in the middle of the lever. So in this case, what's in the middle is the resistance. Axis is on one end, and the force is on the other end, and the resistance is in the middle. If it were flipped around so that the force were in the middle with the axis on one end, it would be a class 3 lever. If the axis were in the middle, it would be a class 1 lever. But back to our discussion of torque here, and with our discussion of torque, we have to, now that we kind of know what it is, look at the formula for torque. So torque equals, in its most general terms, force times distance. What we mean by that is the torque, or the rotational force around this axis, is the product of whatever the force is, in this case the weight of the object or the forces is applied on this end of the lever, times the distance from the axis. And when we say the distance from the axis, what we really mean is the shortest possible line from the shaft of the vector, or the path of the vector, to the axis. And that shortest possible line is always going to be perpendicular to the vector itself. So in this case, this would be the distance around which this resistance works. In the case of the force on the end over here, we have to extend it down a little bit so that we can draw a perpendicular line to the axis. But once we've done that, then we can also draw a perpendicular line from the axis to this line of force expressed by, for example, somebody pulling up on the handles of the wheelbarrow. So to then kind of put this together with our formula, torque equals force times distance. For our resistance, we have the resistance, and then we have this distance here, which is called the resistance arm. And so the torque provided or produced by the resistance, that is the weight in our wheelbarrow, that torque is going to equal the resistance, that's the force, times the resistance arm, that is the perpendicular distance from this vector to the axis. On the other hand, the torque produced by our force out here on the end of the lever is going to equal this force, and we call it a force when it's the thing that's doing the moving, a resistance when it's the thing that's being moved, times the force arm being this distance right there. So that is kind of how we apply the formula for torque to this particular lever system. Now let's add some numbers to this just to kind of see how this works. So let's say for our resistance here, in our wheelbarrow we have a sack of sand or something that we're moving, and that's going to weigh 10 pounds. Okay, so that's our resistance. We can plug that in right here. Okay, 10 pounds. Okay, and then we also have this resistance arm here, and again, going with the analogy of this is kind of like a wheelbarrow, let's just go with things that make sense about like that. Let's just say this resistance arm is 2 feet. So 2 feet long, so we can put that in here. This is 2 feet. Okay, so then the torque created by this resistance acting around this axis, which is the axle of our wheelbarrow, would be 20 foot-pounds. So that's the torque that this resistance is applying around this axis to that lever. So that's the kind of resistance torque. Now let's talk about what's happening over here as we try to lift our wheelbarrow up. So we know that the resistance is creating 20 foot-pounds of torque around this axis. And I want to know, well, how much force do I have to apply here at the handles in order to meet that or overcome it so I can actually pick it up and roll it along? Well, let's figure that out. What do we know? Well, we don't know the force, but let's say we do know the force arm. The resistance arm was 2 feet. That force arm looks about twice as much. So I'm just going to call that force arm 4 feet. Okay? And in order to just balance the torque from the resistance, I know that I need 20 foot-pounds of torque produced out here just to equalize it. Okay? So if 20 foot-pounds, I know my force arm here, along here is 4 feet. Well, what is my force going to be? Well, that math is fairly straightforward to do, and basically what I need is then 5 pounds of upward force on the handles to lift my 10-pound load in the middle of the wheelbarrow. Anything more than 5 pounds will actually lift it off the ground. 5 pounds will just kind of hold it in its steady state. Anything less than 5 pounds, then I have pressure from the feet of the wheelbarrow on the ground. One more thing before we let go of this is the whole idea of mechanical advantage. So here again we have a second-class lever, and playing around with the various torques and how do we get them equal and that kind of thing. Let's talk about mechanical advantage, because that's one other thing. You may remember that the formula for mechanical advantage is force arm divided by the resistance arm. Okay? Applying that to our example here, well, our force arm was 4 feet, and our resistance arm was 2 feet. So our mechanical advantage then is, in fact, 4 divided by 2, or simply 2. Which makes sense with the numbers that we just looked at earlier, because basically for every 2 pounds of resistance that we lifted, we only needed 1 pound of force to actually lift it up off the ground. So that, in a nutshell, is one way of looking at torque and in a lever system and mechanical advantage. But now let's apply this to the human body a little bit, because that's the reason we're really learning this, is to figure out how this works in the human body. So in the human body, let's just look at how this would apply, for example, to somebody lifting something up in their hand, flexing their elbow. So first up here we have a humerus, and down here we're going to have the ulna. And actually I think we'll just kind of look at that as the forearm, ulna and radius together. And then over here we have the hand, expertly drawn, and in the hand we're going to have a weight. So here's our dumbbell weight in the hand. Okay. And so that's providing the resistance. And over here we have the biceps muscle, providing the lifting power. Now when we apply it to a biomechanical example like this, it's all the same concepts, but we use different terms. So you'll remember the formula for torque in general was that torque was force times distance. In the biomechanical model, we kind of rename what this force and distance is, okay? So we have forces or torques created outside the body, i.e. torques created by the weight. We call those external torques. Torques created inside the body, that is by the muscle, are internal torques. So here we have the torque created by the weight, and that is expressed by external torque equals external force times the distance, and the distance we call the external moment arm. For the biceps on the inside of the body, it's an internal torque, and that is equal to the internal force multiplied by the internal moment arm, or the distance from, perpendicular distance from that force vector to the axis. So how does this actually work out? Well, where's the axis of movement? The axis of movement is always in the convex member of the joint. So that is going to be right down the center of the trochlea here at the distal end of the humerus. And then we have to look at the perpendicular distance for that. So let's look at the external torque first. For the external torque, let's just say this is a 7-pound weight, And then for the distance, for the external moment arm, we have to draw a line that is perpendicular to the force vector for this 7-pound weight to the axis. Well, the force vector is pretty easy. It's from the center of gravity, wherever that is, and straight down, because that's how gravity works. A line drawn perpendicular to that to the axis of motion is going to look something like that. And so this then is our external moment arm. Here we have our external force. Okay? For the internal torque, internal force, and internal moment arm, we got to look at that yet. So here's my biceps, and it's pulling up like this from its attachment, actually to the radius, but then up toward its proximal attachments on the shoulder blade, on the scapula. And if I draw a perpendicular line, so here's my force vector for this basically, and if I draw a perpendicular line from that force vector to the axis, it's going to look something like that. Okay, so this distance here then is the internal moment arm, and this force here, represented by that vector, is the internal force. You notice the internal moment arm is not the distance from where the muscle attaches to the axis, it's the perpendicular distance from the line of force to the axis. All right? So again, let's look at how this will work out in the real world. Here we have an external force. A dumbbell weighs 7 pounds. Let's actually start to plug some of these numbers in. So my external force is 7 pounds. My external moment arm, let's just make it really easy and say that this distance from the axis to the center of gravity of that weight is 1 foot. I like easy numbers. Okay, 1 foot. All right. And so that is going to produce then an external torque of 7 foot-pounds. Now let's say we want to just manage to hold it there so it's not moving, not coming up, not going down. Then we have to have an internal torque that matches that. So if our internal torque is also going to be 7 foot-pounds, all right. Our internal moment arm is kind of already determined just by the nature of how this attaches and the angle of the joint. Just to make it easy, let's say that internal moment arm is 3 inches, which would be then, to keep the units the same, 1/4 foot. All right. And what we're wondering then is, well, how much force does this biceps have to generate in order to equal the torque created by the 7-pound weight in my hand? Well, if you want them to be equal, you just make these two formulae equal, and then again, it's fairly straightforward. We've kind of already done that here. We just have to solve for our internal force. And if you do the math, that then is going to be 28 pounds. So in order to lift this 7-pound weight, because my internal moment arm is 1/4 of my external moment arm, my biceps has to generate 28 pounds of force just to hold it steady. Anything more than 28 pounds of force, then my internal torque is going to exceed my external torque, and I'll lift it up. Anything less than 28 pounds of force, the external torque will be greater than the internal torque, and the weight will go down. So just to relate those then to other concepts that we have learned in terms of muscle contractions, okay? When your internal torque is equal to the external torque, So for example, I have my 7-pound weight here. If my internal torque is equal to my external torque, the weight just stays there and it doesn't move. All right, you'll notice that does not mean the internal force is the same as the external force. It just means that the torques are equal. If, on the other hand, my internal torque is actually greater than my external torque, the internal torque wins, and when the internal torque wins, I'm going to lift that weight up in the air. Finally, if my internal torque is less than the external torque wins, so the weight wins, and that weight is going to lower slowly to the ground. How slowly depends on how much the external torque exceeds the internal torque. This presupposes, however, that the internal torque is indeed greater than 0, because if my internal torque was 0, it wouldn't slowly lower at all, it would just drop right down. So that, in a nutshell, is torque, some torque concepts applied to levers, and then torque concepts applied to a biomechanical example.